Hello, my name is Mr. Asprey and this is another EDEXCEL paper. This is June 2018. This is paper 2 and this is about to get boshed. Here we go. Right, let's get started with find g of 5. So that means what I need to do is I need to substitute 5 into g, which is going to give me 2 times 5 plus 5 over 5 minus 3, which is 15 over 2. And then that needs to go into g again. So that will be g of, let me write g of 5 is equal to g of 15 over 2, which is equal to, let's just get the calculator out, shall we? So 15 over 2 is 15 over 2, good. So we do, so let's just go 2 lots of the answer plus 5 over the answer minus 3. 40 over 9. Perfect. That's part A. Part B asks us to state the range of G. Okay, tricky. So let's look at the domain first. The domain tells us that we have to substitute in values of 5 or more. And we know what G of 5 is. It's 15 over 2. So the upper end of the domain is just like a really huge number. Let's see what happens when I sub in a really huge number, like, I don't know. What is that? 1,000, 100,000, sorry. Well, I do 2 lots of the answer plus 5 over the answer minus 3. And let's see what we're going to get. We're going to get something approaching 2. So as this function grows, it gets larger and larger, it's actually going to tend to 2. So as x tends to infinity, g of x tends to 2. So that means the range is between 2 but not equal to. Can't possibly equal it because it's just going to get closer and closer to it. And the upper range is 15 over 2. And that can be equal to because we are allowed to substitute in 5. Okay, part C. Find the inverse of g of x. So what we do is we set it equal to y, like so. And then we swap x for y, because the inverse function takes the outputs and turns them into inputs. So it turns the x's into y's, or sorry, the y's into x's. So we swap over, all of the x's become y's and all of the y's become x's. So we have this. We then need to rearrange to make y the subject. So I do that by multiplying through by that denominator. And then I will expand out. And then I bring all the y's onto one side. So I will bring them all over to this side. So I'll minus 2y, and I'll move the 3x to the other side, becomes a positive. Then I can take out a factor of y. And now y only appears once, so I can divide through and I get an expression for y, which is going to be the same as my inverse function. So 3x plus 5 over x minus 2. And it asks for the domain. So really interestingly, recently on EDEXCEL papers, they ask you for the inverse function, but they don't say state the domain. But they do require you to state the domain in order to get the full marks. So that's something they've changed from papers now. They don't write this green bit, but they do require you to write it anyway. So what is the domain? Well, the domain of the inverse is the range of the original. And the range of the original we've already worked out. It was between 2 and 15 over 2. And for a domain, we always write x. So this is my final answer. Question number 2. We have that the point A has that position vector, B has that position vector, the point C has this position vector, and it says that D is the point such that A to B is equal to B to D. Find the position vector of D. Okay, well let's first off find A to B because that is given as part of the question, and A to B is O to B minus O to A. And this is therefore equal to, let's write them as columns, I prefer it as columns, 4 minus 2, 3, minus 2, 3 minus 4. Okay, so that gives me 2, and it gives me minus 5, and it gives me 7. Okay, great. So what is B to D? Well, B to D, in the same way as what we wrote out before, would be O to D minus O to B, like so. So I can rearrange this to get O to D, because that would be B to D plus O to B. So what we're looking for is the position vector of D, which is O to D, and B to D we know is the same as A to B, which we've already worked out is 2 minus 5, 7. So we just need to add on O to B, which is 4 minus 2 and 3. So this gives me 6 minus 7 and 10. And seeing as they give all of the original position vectors in this particular form, I would feel obliged to write it in that form as well. So 6i minus 7j plus 10k. Always give your answer in the form that the question gives the information in, even though I prefer columns. Just got to cater to the crowd. Okay, next it says, given that A to C, the magnitude of A to C is equal to 4, find the value of A. Okay, well we can get started by finding out what A to C is. And just like before, A to C is O to C minus O to A. Okay, so let me just grab some more space. So this is O to C is A, 5 and minus 2, minus O to A we know is 2, 3 minus 4. Okay, so this gives me A minus 2, it gives me 2, and it gives me 2 again. Yes. Now we're looking at the magnitude of that, which is going to be all of its components squared and then overall square rooted. So that will be A minus 2 squared plus 2 squared plus 2 squared, and we were told in the question that was all equal to 4. So let's get rid of the square root. We can move that over to the other side. These are 4 and 4, which make 8. And when I square both sides, I get 16. Okay, I could expand out this bracket and then solve the quadratic, but actually it's easier just to minus the 8 to that side to give us this. Square root, which gives me plus or minus the square root of 8. And then just add the 2 on. So it's 2 plus or minus the square root of 8, which is the same as 2 plus or minus 2 root 2. And then we check the most important part. The most important word in the whole of the A-level maths paper is this one, value, and whether or not it is plural or singular. And in this case it is singular, and I've got two answers, so I need more information, and the information is that A is less than 0. So that means that the final answer must be 2 minus 2 root 2, as A is less than 0. Bosh. Question number 3. If M and N are irrational numbers that are not equal, then Mn is also irrational. Disprove this statement by means of a counterexample. Okay, so if m is equal to the square root of 20 and n is equal to the square root of 5, then m times n is equal to root 20 root 5, which is equal to root 100, which is equal to 10, which is rational. So we've disproved it, basically. Yeah, done. Don't think I need to write anything else. Okay, next we've been asked to sketch this graph. Okay, no problem, can do that. There's my axes. In fact, actually, I don't need to go into the negative part at all, because this is going to be an all positive graph. The modulus of x looks like this, because the modulus function turns all of the values positive. So y equals x normally looks like this. That's not a very good graph, is it? It's not in line. Y equals x normally looks something like this, but the negative parts below the axis get reflected up, because the modulus always turns it positive. Okay, but then we're also plussing on 3, which means every part needs to move, every coordinate needs to move up by 3. So it's going to look like this. And we can make sure that we label this part here number 3, and we say that this is y equals the modulus of 3, the modulus of x plus 3. Okay, part 2 asks us to explain why the modulus of x plus 3 is always greater than or equal to the modulus of x plus 3. Right, so what I could do is, given that I've already drawn one graph, I could just draw the other graph. And that would look like the graph of just y equals 3x, so without the modulus sign at all. I could just draw that. And that would look something like this. But then the negative part gets rebounded, so it would look like that. So then I would have to delete this part here. Okay, and we can see that when x is greater than 0, they are the same. So the modulus of x plus 3 is equal to the modulus of x plus 3. And when x is less than 0, we can see that the blue graph is greater than this one. So we can therefore say, therefore x plus 3, like that, is always greater than or equal to x plus 3 for all x. Perfect. Okay, next question, and we've got a horrible series here, but what we can do is we can split it up. So we can split it up into the series up to 16 of just 3, the series of up to 16 of 5R and the series up to 16 of 2 to the R, and then we can add them together at the end. Okay, so what is the first one going to be? Well, that's just 3 16 times. It doesn't change, and we just do it 16 times. So that's going to equal just 3 times 16, which is 48. The next one, when R is 1, we get 5. Then when R is 2, we get 10. And then when R is 3, we get 15. All the way up to when R is 16, we get 80. So this is an arithmetic sequence of which the formula is n over 2, 2a plus n minus 1d to find the summation. So we're going to have to use that formula, which you are given in the formula book. So n is 16, so it's 16 over 2. The first term is 5, so 2 times the first term, 2 times a, is going to give me 10. And then n minus 1 is 15, and that's times by the difference between the terms, which is 5. Okay, so 15 times 5 is 75, plus 10 is 85, so we need to do 85 times 16 over 2 is 8. So 680, whoops. Okay, the next one, when R is 1, we get 2 to the 1, which is just 2. When R is 2, we get 2 squared, which is 4. And then when R is 3, we get 2 cubed, which is 8. And then we're going to get blah, 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 all the way up to 2 to the power 16, which I don't actually know off the top of my head. But just for the... Anyway, so 65,536. Okay, well, anyhow, this is a geometric sequence, and the summation for a geometric sequence is, that's the arithmetic one, the geometric one is a r to the n minus 1 over r minus 1. Or sometimes you can write it the other way around, but it's fine. So a is 2, r is the ratio, and we're timesing by 2 each time. N is 16 minus 1 over 2 minus 1. Okay. Oh, sorry, I put r there. I meant to write 2. Okay, well, so it's 2 lots of, I literally just did that 2 to the power of 16 as my last answer, minus 1, and then divided by 2 minus 1, it is 1. So we get this, 131,070, and then we need to add these 3 up. So I just need to add on 680, and I need to add on 48, and I get 131,798. Perfect, that is exactly what they asked for. Job done. Okay, next. We've got this sequence here, which is defined as a recurrence sequence. So we know the next term is the last term reciprocal, so 1 divided by the last term. And u1 is 2 over 3. Okay, so if u1 is 2 over 3, then it means that u2 is the reciprocal of that, which is just 3 over 2. And then u3 is the reciprocal of that, which is just 2 over 3. So this is going to have order of 2. It's have order or period, you can use either word, of 2. It's just going to repeat every 2. So to find the sum to 100, well, that's relatively straightforward, really. The sum to 100 is going to be 50 lots of 2 over 3 plus 3 over 2. because there's going to be 50 pairs of these two numbers just repeating, and that's going to give us 100 terms. So 2 over 3 plus 3 over 2 is 16 over, is 13 over 6, so it's 50 times 13 over 6. So just multiply that by 50 and we get 325 over 3. Job done. Okay, Newton-Raphson question, and it says that this has exactly one root. It says show that this equation, the Newton-Raphson formula, can be written like this. Okay, so let's remind ourselves what the Newton-Raphson formula is. It is xn minus the function subbing in xn over the derivative function subbing in xn. Okay, so let's do that then. So let's write xn minus, when I sub it into the function, I just get the function itself, which is 2x cubed plus x squared minus 1. And then the derivative function, well, that will be 6x squared, and it will be 2x, and that's it. Okay, now I've got to write this with this denominator so I can subtract the 2. So I write xn multiplied through by this all over it will then allow me to subtract these two fractions. Okay, so I've got a common denominator now, and when I multiply this out, I'm going to get 6x cubed plus 2x squared. I'm going to get a minus 2x cubed. I'm going to get a minus x squared, and I'm going to get a plus 1. And I'm pretty sure that's going to give me yeah, what I want. Perfect. Yeah, so 4x cubed plus 1x squared plus 1 over 6n squared, sorry, 6x squared plus 2x. Perfect. Right, using the formula given in part A, with x equals 1, find the values of x equals 2 and x equals 3. Okay, I'm going to get a bit techie here. I'm going to go into recursion mode, and I'm going to delete that one, and I'm going to write in the formula. So 4an cubed, should have hit a bracket first, not a bracket, a fraction, 4an cubed plus an squared plus 1 over 6 an squared plus 2 an, riveting. Set, I want to start with the value of, let me just quickly check again, 1. Okay, great. So make that 1. First 6 is fine. Table. So I get 0.75 and what looks like 2/3. So x1 equals 0.75, x2 equals 2/3. Perfect. Part C, it says explain why we can't use x1 is equal to 0, and that's because we would be dividing by 0, and it's because the gradient function will have a turning point there. so there is a stationary point at x equals 0. And that's enough. We can't use the Newton-Raphson formula at a stationary point or very close to a stationary point. Okay, question 6. We've got a function, calculate f of 2. Don't mind if I do. That should be fairly straightforward. I will write out the working, I guess. I feel like this is kind of like 3 marks, as in like FREE marks. Okay, so minus 3 times by 8 plus 8 times by 4 minus 18 plus 10. Oh, lo and behold, it's 0. Okay, so the next part asks you to write f of x as a product of 2 algebraic factors. Well, we know from factor theorem that now x minus 2 is a factor. So what I'm going to do is I'm going to do a bit of algebraic polynomial division in order for me to find another algebraic factor. Okay, so how do we do algebraic polynomial division? Well, some people love it, like myself. Some people hate it. We look at the lead term. In this case, it is minus 3x cubed, and the lead term of the divisor, which is x, and we divide that by that, which gives me minus 3x squared. We then multiply that by our divisor, x minus 2. So that gives me minus 3x cubed, and it gives me plus 6x squared. So that's in the bag now. We're definitely using that. So we need to subtract it from our polynomial to see what's left over. Well, we have 2x squared there, and that 9x is not being used, so that can come down as well, and so can the 10. Okay, now we do it again. Now our new lead term is 2x squared. So let's divide that by our divisor x, and that gives me plus 2x. Okay, now we've got that in the bag, we can multiply it through by the divisor to see what that gives us. That gives me 2x squared minus 4x. Okay, right, again that's in the bag, so let's subtract that to see what we've got left. Be careful of the negatives, but minus 9x minus 4x is minus 5x. Bring the 10 down for the party, and then finally the new lead term is minus 5x. So divide that by x gives me minus 5, and that, when I multiply through, should give me minus 5x plus 10. Perfect. Perfect division. Lovely jubbly. So this means that over here I have quite a lot of x minus 2's. In fact, how many x minus 2's do I have? Well, I have minus 3x squared of them, I have plus 2x of them, and I have minus 5 lots of them. And that is equal to f of x. Perfect. There we go. Job done. We have written it as a product of 2 algebraic factors. Using the answer to the last one that we've just done, prove that there are exactly 2 real solutions to this equation. Okay, lovely question that, absolutely lovely. So that equation, equation here is very similar to the f of x that we have. In fact, what is the difference? Well, x has been replaced by y squared. So x has been replaced with y squared. So let's go down here to this and replace the x with y squareds. So we have this. We have, that will make to the power 4. And that is equal to 0. Because we're saying that, yes, here we go, you can see it up here, it says that it's equal to 0. Fantastic. Okay. How do we solve this now? Well, we can say that y squared equals 2, that comes out of this bracket, and from here we have two solutions. Let's just write them down. Y is equal to plus or minus root 2. Now, does this one have any solutions? Well, it is a quadratic. You can see here that it's a quadratic factor. So let's check the discriminant to see if it has any factors. So the discriminant is b squared minus 4ac, which in this case is equal to 2 squared minus 4 lots of a is minus 3 and c is minus 5. This gives me 4 minus 60. Yes, which is minus 56. Okay, so we can say that there are only two solutions, or should I say, sorry, two real solutions, y equals plus or minus root 2. As this part up here, there are no real solutions. So the only two solutions come from this bracket right here. Okay, part C, it says deduce the number of real solutions between 7 pi and 10 pi to this equation. Okay, so this equation essentially is exactly the same as the original one set equal to 0. You just have to multiply through by minus 1 and replace the x's with tan thetas. So it is the same equation, and we know that this original one has only one solution, that is x equals 2. Remember, the one we've just done has two solutions because it's squared. That's why you get the plus or minus. But for this one, there's only one solution. So that means that tan theta will equal 2 is the only solution. And then how many solutions do you get for tan in between 7 pi and 10 pi? Well, for tan, there is a solution every 180 or every pi, because the graph looks like this. So for and that's up to pi. So for every pi, you're always going to get, or you're guaranteed to get one solution. So between 7 pi and 10 pi, that's 3 pi. So you'd expect to get 3 solutions. So the answer is 3 solutions. Okay, next question, and we have a classic trig question. So we have 4 sine x is equal to sec, and sec is 1 over cos x. Okay, so let's multiply up to get 4 sine x cos x equals 1. And of course we know from our double angle formula that 2 sine x cos x is sine 2x. So this is twice that, so it is 2 sine 2x. So therefore we have sine 2x equals a half. And of course we know that sine to the minus 1 of a half is 30 degrees, or pi over 6. And the other value will be pi minus that, which will be 5 pi over 6. And then if we divide both sides by 2, we get x equals pi over 12, and we get x equals 5 pi over 12. And that will be all of our solutions. Well, that was quite neat that you didn't have to use a calculator for that one. That was nice. Okay, the next question is a bit trickier because there's no real trig identity that we can use to solve this. Like if that was a 0, for example, we could move the cos to that side, divide through by cos, and we'll get a tan, which would be nice. But the fact there's a 2 there is making it really annoying. But what we could do is we could convert into r sine theta minus alpha. We could convert the 5 sine theta minus 5 cos theta. Now there's a trick to doing this, and that is making sure that we're going in sine, so we put the sine first, and when we do r sine, the sign in between has to be the same for cos. It swaps over, so we're good there. And what we do is we label this one a and this one b, so the coefficients of the sine and the cos. And then we can say that the r value is the square root of a squared plus b squared, and the alpha value is always tan to the minus 1 of b over a. Okay, so now we can convert this equation into, well, r is going to be equal to the square root of 5 squared plus 5 squared, which is root 50, which is 5 root 2. And alpha is going to equal tan to the minus 1 of 5 over 5, which is tan to the minus 1 of 1, which is 45 degrees. And notice we're in degrees now. It's very cheeky from EDEXCEL to swap mid-question. Okay, so my equation now becomes, rather than 5 sine theta minus 5 cos theta, I can write 5 root 2 times by sine of theta minus 45 is equal to 2. Lovely. So dividing through, I will get, I can't be bothered to rationalise that denominator. 5 over root 2, it's quite lazy. Root 2 over 5. Okay, yeah, we can. So then what we're going to do is sine to the minus 1, checking we're in degree mode, which we are. So that gives me that theta minus 45 is equal to 16.4. And of course, as soon as you press sine to the minus 1, you must find the second solution. For sine, it is 180 minus. So 180 minus that solution. Always do that before you do anything else. Is 163.57. And then we just add 45 to both of these. So I'll just add 45 to this one while we're there. It says 1 decimal place, so that would be 208.6. And then we'll do the 16.4, add 45. I can do that one, can't I? Come on, surely. 61.4. Bosh. Tricky question that, because normally if you need to use r sine theta minus alpha or r sine theta plus alpha, they will give you a hint, but no hint there. Okay, question number 8, and we've got this graph showing the trajectory of a rugby ball. Blah de blah de blah. There are certain points which we're told. It reaches a maximum height of 12 meters. And it hits the ground at a point 40 meters away from where it was kicked. Okay, and it's asking us for a quadratic equation. So the quadratic equation would be h equals ax squared plus bx plus c. That's quadratic. And the points that we know it goes through the origin, we could tell that from the graph. We know it goes through 40, 0, because that's where it ends up. And we also know at the halfway point, which is where the maximum height will occur, is 12. Okay, so subbing in 0, 0 is going to give me 0 is equal to, well, 0 plus 0 plus c. So therefore I know that c value is 0. Then subbing in 40, 0 is going to give me 0 is equal to a times 40 squared plus b times 40, so 40b. And we know that c is 0. Okay, so that gives me, what, 1600a plus 40b equals 0. And then using finally the third point, I will say that, well, the height is 12 and the x value is 20. So 20 squared is 400, so 400a, and then plus 20b. Okay, great. So what we'll do is we'll times this one by 2. And then we will subtract this one and this one. Oops, that should be an A there. Okay, perfect. They line up perfectly now, so we can subtract them, solve it simultaneously, and that is going to give me minus 24 is equal to 800A. So A is equal to minus 24 over 800, which simplifies to minus 3 over 100, or minus 0.03. Okay, so now we need to sub back in to get the b term. So 24 is equal to 800 times by a, which we know is minus 24 over 800, or minus 0.03, but this is going to cancel nice and neatly, and then plus 40 times b. So we get 24 is equal to minus 24 plus 40b. So that gives me that 48 is equal to 40b. So b is equal to 48 over 40, which simplifies to divide through by 8, 6 over 5, which is 1.2. So we need to actually write down our final answer, and that is that h is equal to minus 0.03 x squared plus 1.2 x, and that's it, done. Okay, the next part says that the ball passes over the horizontal bar of a set of rugby posts that is perpendicular to the path, and the bar is 3 meters above the ground. So let's imagine that this here is the 3 meter rugby post. It says find, using your equation, find the greatest horizontal distance. So this distance here of the bar from O. Okay, so we just basically need to substitute into our formula. So let me just get rid of this working here. And what we could do is use our formula and use the fact that the height is 3. So h equals 3 is going to give me 3 equal to minus 0.03 x squared plus 1.2 x. So set that equal to 0. I'll move it all over to the left side to make the x squared term positive. Plus 3 equals 0. Okay, we need to solve that using our calculators. So this will be, I'll just go into the equation, polynomial degree 2 and we've got 0.03, we've got minus 1.2, and we've got 3. Okay. Right, so not nice numbers, but anyhow, it's going to be the larger one because it's obviously the second time it gets to the 3 meter line. So we're going to go with x is equal to 37.32. That should do it. And then finally, one limitation of the model. Well, what we've done is we've assumed that the rugby ball has no like dimensions. So the limitation is that the rugby ball is a particle and has no length or width. Okay, first principles. The derivative of cos is equal to minus sine. Well, the formula for the derivative function, which is given to you in your formula booklet, is the limit as h tends to 0 of f of x plus h minus f of x all over h. So let's define the function we are trying to differentiate as cos x, and then let's figure out what f of x plus h will equal. Well, that will be cos of x plus h, which using the compound angle formula is cos x cos h minus, we always swap the sign, sine x sine h. Okay, so that's helpful. So now what we can do is we can substitute into our formula. So the derivative function, like I said up here, is equal to the limit as h tends to 0 of f of x plus h, which we've just shown is cos x cos h minus sine x sine h, minus f of x, which we defined as cos x, all over h. Okay, so what we can do next is we can factor out a cos x. So we can have cos x. So how many cos x's are there on the top line? Well, there is one here, which is times by cos h, and there's also one here, or negative one here. So when I take out that as a factor, it becomes minus 1. And then we also have over here minus sine x sine h, and all of that is divided by h. Okay. So next we need to maybe split this up. Yeah, let's split this fraction up, and let's use the fact that this is going to, we need to find this and we need to find this. Okay, so we have cos x cos h minus 1 over h. So we can write it like that, minus sine x of sine h over h. So just take a moment just to double check what I've done there and to see how these are equivalent. And now we can use these blue things up there, and we can say that as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. Therefore, f of x is equal to, so f dash of x is equal to, well, let's let's double check this. So this tends to 0, which means that is just completely wiped out. And sine h over h tends to 1, which means that is becoming 1. So all we're left with is just minus sine x. And we're good. Love a bit of first principles. Oh, this has got to be the worst question possibly ever. Like, not only do you have to think about someone putting a mint in their mouth and sucking on it, but also, like, there's so little to go on. Anyway, let's give it a go. A spherical mint of radius 5 millimeters is placed in the mouth, and sucked. 4 minutes later, the radius of the mint is 3 millimeters. Okay, so what can we take from that? We could take that when t equals 0, r equals 5, and when t equals 4, r equals 3. In a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. Okay, so that can get started. So it says the rate of decrease of the radius. So the rate of decrease is dr by dt. The rate of decrease of the radius, sorry, is dr by dt. And that's inversely proportional to the radius squared. Oh, sorry, so inversely proportional, I just write 1 over r squared. Okay, so we can write this now as an equation using k as a constant. We know that from our GCSE work. Okay, so using this model and all the given information, find an equation linking the radius of a mint and the time. Okay, so we've got enough stuff now. So what we could do is we could separate the variables here. So the first thing I would do always is multiply through by dt. So now the right hand side we want the like the t's, and the left hand side we want the r's. So that r squared needs to come over to the other side. So it becomes r squared dr is equal to k dt. We can then integrate both sides with their respect to their given variables. So integrating r squared with respect to r gives me 1/3 r cubed. And then integrating k with respect to t, well, k is a constant, so it could be like 4. When you integrate 4, you get like normally 4x, but because it's respect to t, it would be 4t, and because k is unknown, we're just going to call it kt. And plus another constant of integration, because whenever you integrate, you get constant plus c. We don't need to write it on both sides because the arbitrary constant c is enough to cover whatever the two constants would be together. Okay, now we use our initial conditions. So initial condition 1, let's get that in there. When t is 0, and r is 5, so we're going to get 1/3 times by 5 cubed is equal to t is 0, so that's equal to c. Great, so that means that c is 125 over 3. Okay, initial condition 2. I shouldn't call it initial condition, it's just a condition, it's a boundary condition, because it's not, in this case, it's not initially, it's not when t is equal to 0. But that's just pedantics. T equals 0. Sorry, t equals 4. Sub it in, and r equals 3, so I get 1/3 times 3 cubed is equal to 4k plus c, which I already know now is 125 over 3. So this gives me 9 is equal to 4k plus 125 over 3. So I need to find k, so I will do that on my calculator, and I will do 125 over 3 No, I won't. Oh gosh, stop it. I'm messing this up a bit. No, I'm not. 9 minus, yes, that's good, and then divide that by 4. Okay, so I get some very nasty looking numbers here. But nevertheless, oh god, it said you should define the variables you use as well. Holy moly. Okay. So we get that 1/3 r cubed is equal to minus 49 over 6 t plus 125 over 3. So I might want to tidy that up by multiplying it through by 6, because that just looks horrible, which would give me this. And in terms of the variables, r is equal to the radius of the mint in millimeters, and t is equal to the time in what was it, minutes, I think. Yeah, minutes. Okay, I should have written time in minutes from when the mint was first put in the mouth. Lovely. Okay, hence find the total time taken for the mint to completely dissolve. Give your answer in minutes and seconds to the nearest second. Okay, well, we've got this lovely formula now which we can use, and what we need is for it to completely dissolve is the r to equal 0. So when r equals 0, we get 0 equals minus 49t plus 250. So t is equal to 250 over 49. Okay, which is going to be 5.10, which translates to 5 minutes. And then to convert that decimal, I'll take away the 5, and then I'll multiply it by 60 in order to tell me how many minutes that is. Sorry, how many seconds. So that's 6 seconds. Okay, perfect. Suggest a limitation of the model. Well, the model suggests the mint is sucked evenly and consistently, which is probably not going to be the case. Okay, question 11 looks like just classic partial fractions, so I'd be really happy to get this type of question because it's all formulaic really. So multiply through by that left-hand denominator, which gives me x minus 3 and 1 minus 2x times by a. And because the b has been divided by x minus 3, when I times through the x minus 3, that will cancel, but we still have the 1 minus 2x. And the same with the c, the 1 minus 2x will cancel, but we have the x minus 3. Great. And then what we do is we just say let x equal 3. That's going to cancel out some of these brackets. So when x is 3, the left-hand side becomes 1 plus 33 minus 6 times 3 squared, which is 9. So it becomes minus 20. This will completely cancel out because the x minus 3 bracket will get wiped to 0. The b term will be multiplied by 1 minus 6, which is minus 5. And the c term will also get completely wiped because there is an x minus 3 bracket there. Okay, great. So this clearly shows that b is equal to 4. Okay, next we would let x equal, well, we need to cancel out the other bracket, and a half would do that perfectly. Yes, it would. Yep, double checking. 1 plus 11 times by a half minus 6 times by a half squared gives me 5. Lovely. The a bracket will get wiped, the b bracket will get wiped, but the c bracket won't, and we will have c multiplied by a half minus 3 is minus 2.5. So that tells me that c must equal minus 2. Perfect. And then finally, you can sub in anything now to find the third one. X equals 0 is obviously just the most easiest one to do. So the left-hand side will give me just 1. This a term here will be times by minus 3, and it will be times by 1. The b term will be times by 1, and we know b is already 4. And the c term will be times by minus 3, and we know that it is minus 2. So we get 1 is equal to minus 3a plus 4 plus 6. So that tells me that minus 3a is equal to minus 9. So a is equal to 3. Wallop. That is just a lovely bog standard 4 marks. If you know how to do it, you're getting those marks. Okay, next it says prove that f of x is a decreasing function. Well, in order for it to be a decreasing function, we would need to differentiate this. And then, once it's been differentiated, show that the gradient function is always negative. So the gradient is always negative, so it's always decreasing. Okay, now this is a part B, so we must be looking to use part A somehow. And let's write the function out in terms of its partial fractions. Yes, let's do that. That sounds very sensible. So f of x is equal to a, which is 3, plus 4, and I'm just going to bring this bracket up like that, and then minus 2, lots of this bracket, I'll bring it up like that, just makes it easier to differentiate. Okay, so now we are going to differentiate. 3 differentiates to 0. How do I differentiate a bracket like this? Well, I do the power times by the coefficient, which gives me minus 4. I keep the bracket the same. I drop the power down by 1, and then I times by the derivative of the bracket, which is just 1. Okay, let's do exactly the same. I times the power by the coefficient, that gives me plus 2. I keep the bracket exactly the same. I drop the power down by 1, and then I times by the derivative of the bracket, which is minus 2. Okay, so what does this give us? This gives us minus 4 over, I'm going to put it on the bottom now, because it's x minus 3 squared, because that negative power brings the whole bracket to the bottom. And then we're going to have another minus 4 on top here, and we're going to bring this bracket down to the bottom as well, like that. And that is very neat, because we know that x minus 3 squared and 1 minus 2x squared are always positive. Therefore, f of x is equal to minus 4 over x minus 3 squared plus minus 4 over 1 minus 2x squared is always negative. Therefore, f of x is always decreasing. Bosh. So again, because the denominator is always positive, the numerator is always negative, the whole expressions must be negative, so therefore it's always decreasing. Okay, getting tricky with it. Here we go. Cos 2 theta could be transformed into many things, so I'm actually going to start over this side. So tan theta sine 2 theta is the same as sine over cos is tan, and that's times by 2 sine theta cos theta, because that's the double angle formula for sine 2 theta. Okay, this is, we're going to get cos theta cancelling, so I'm going to get 2 sine squared theta. Okay, and that tells me which one to use. I'm going to use the one which uses sine squared, and that is 1 minus 2 sine squared theta. When multiplying out, I get 1 minus 1, which is 0, and I just get minus times a minus is a plus, so I get 2 sine theta. So this was the right hand side, this was the left hand side, and I can write right hand side equivalent to left hand side QED. Right, hence solve for this range. The equation sec squared minus 5 1 minus cos 2 theta is equivalent to tan squared 3 tan squared sine 2 theta. Okay, so I suspect I will need to replace this with this. Let's do that. So sec squared x minus 5 is now multiplied by tan theta sine 2 theta, or tan x, sorry, sine 2x, and that's equivalent to 3 tan squared x sine 2x. Okay, we can remove the sec squared by replacing it with the identity, which is sec squared x is equal to 1 plus tan squared x. So this becomes tan squared x plus 1 minus 5 is minus 4, multiplied by tan x sine 2x, and that's equal to 3 tan squared x sine 2x. Okay. Next, we can divide through by sine 2x, but in doing so, we must be wary and know that this is a solution equal to 0. And we can solve that now. So when I take sine to the minus 1 of 0, I get 0. And the next time that sine is 0 is at pi, or minus pi, going back the other way. But when I divide it by 2, they'll be out of the range because they're not equal to minus pi over 2 or pi over 2. So in fact, x equals 0 is the only solution that comes from that. Okay, next, multiplying out these brackets gives me tan cubed x minus 4 tan x is equal to 3 tan squared x, and we can divide through by tan, which gives me this. But once again, if I divide through by something like that, I need to check to make sure we haven't lost a solution. And this gives me x equals 0, and the next one along will be pi, but again that's out of the range, so it just gives me that solution again. So now this is a quadratic essentially, so I can replace it with a y. Sometimes that helps people factorize and whatnot. So when I factorize this, I will end up with minus 4 and plus 1. So this gives me that tan x is equal to 4 and tan x is equal to minus 1. Okay, so we will go to our calculator for this. We will do shift tan of 4, and we get 1.32. And if we were to add pi to that, then that's going to be out of the range for sure. If we were going to take away pi to that, again, that will be out of the range as well. We could just check that. And if I were to add on pi over 2, I wouldn't get back to 0 yet, so that's out of the range. And finally, let's do shift tan of minus 1, and we get minus pi over 4. And again, if I were to add pi to that, I would get 3/4 pi, which is out of the range as well. So it looks like we've got 3 answers along with x equals 0. Okay, beast question coming up. 10 marker. You don't see these very often. So I'm going to have to split this region up. We need to work out the area of the region, and I've got to split it up because this part is going to be determined by the integral of the curve, whereas this part B is just a triangle. Okay, what we'll do is we'll start with A. So for A, I'm going to need to integrate the curve between 2 points. The first point, the upper bound, is E, and this point in here, we don't quite know yet, but we know that x ln x equals 0 along that line, because it's the x-axis, so it equals 0 there. So the x part tells us that x equals 0 is a solution, and the other part is that x ln x equals 0. So it's the ln x equals 0 gives us our point there, and that's just x equals 1. Okay, so that point there is 1. Okay, so that means in order to find A, I need to integrate between E and 1 the curve x ln x. Okay, now in order to do that, we're going to have to use integration by parts. So integration by parts, we have u and we have dv by dx. Now, which one are we going to pick for which? Well, we always put logarithms in the u slot, and then we will put whatever's left over in the dv by dx slot. Okay, so we differentiate this, which gives us 1 over x, and then we integrate this, which gives us a half x squared. Okay, so now we can say that the integral is, well, it's going to be u times v, just following the formula, which gives me this, and then minus the integral of du multiplied by v, or du by dx multiplied by v, which is going to be, so 1 over x times a half x squared is going to be a half x. Yes, that works perfectly. Okay. Right, so we know that this part is good, but we need to integrate this now. So integrating this up the power to get x squared, divide by 2, is going to give me a quarter x squared. And we're putting in the limits e and 1. Okay, well, when I put in e, I'm going to get a half e squared. I'm going to get ln e, which is just 1, so that's going to cancel out. And I'm also going to get minus a quarter e squared. And then when I put in 1, I'm going to get a half 1 squared, a half times 1 squared, times by ln of 1, which is 0, so that's going to cancel out, minus a quarter times 1 squared. Okay, great. Let's simplify this down then. So that turns to 1, so that leaves me with a half e squared. Minus a quarter e squared is just a quarter e squared. So half minus a quarter is a quarter. So there we go, a quarter e squared, that's that bracket done. This is going to cancel out because ln of 1 is 0. There's 2 minuses there, so that's going to make a plus. And a quarter times by 1 is just a quarter. Okay, brilliant. Right, that's done. Now we move on to section B. So section B, we need to work out this line, don't we? We need to know this line. And that is the line L, and that is normal to the curve. So I'm going to have to find the gradient of the curve first. So differentiating the curve, which is x ln x, I'm going to have to use the product rule because there's two things times together. So the quick way to do the product rule is that you differentiate the first part, x, which gives me 1, and then keep the second part the same. And then we add on, we keep the first part the same, and we differentiate the second part, which is 1 over x. Because ln x differentiates to 1 over x. Okay, great. So this is ln x plus 1, because x times 1 over x is 1. Okay, so what can we do now? Well, we can find out what is the gradient at the point E. That little symbol there just means, that line means we are finding the gradient at the point E, because the x-coordinate of the curve where we want to investigate, which is this part here, is E. So we sub in E. So that's going to give me ln of E plus 1, and ln of E is 1, so that just gives me 2. Okay, great. So now the gradient of the normal at that point EE is minus a half, because it's the negative reciprocal, because it's the normal. Okay, how do we find the equation of a straight line? Well, what we do is we do y minus y1 equals mx minus x1. So we need the gradient and we need a point. And you know, we've got the point EE and we've got the gradient. So it's y minus the y coordinate, which is E, m, which is minus a half, and then x minus the x coordinate, which is also E. So that is L. Sorted. We've got L. Now what do we want from L? Well, we really actually what we want is this point here. If we know that point, then we have enough information to work out the area of the triangle. And that point, of course, is where y equals 0, where it crosses the x-axis. So if I sub in y equals 0, well then what do we get? Well, this equation becomes minus e is equal to minus a half x minus e. Okay, brilliant. We can work out the x-coordinate. Let's times both sides by 2 and multiply out this negative into this bracket, and it gives me this. So therefore, that tells me that the x-coordinate must be 3e. Great. So right here it's 3e. So the gap between e and 3e is 2e. And that's the base of our triangle. So where should I do my working here? Okay, so B is now equal to, A half base, oh, I'm going to sneeze. Right, just spared you from that. Sorry, a half times 3e, and then the height of the triangle, well, is how high up the y coordinate is at the point P. So that's also e. Well, that is e, sorry. Right, so great. Sneeze put me off. Apologies, that's not 3e. The base is 2e. Yes, the base is 2e. Great, so that gives me a total of just e squared. Okay, so we are looking good now because r is a plus b. A, we have worked out, was a quarter e squared plus a quarter, and b is e squared. So in total we have 5 over 4 e squared plus a quarter. Bosh! That was a beast. Okay, beast question to finish off. You've got a differential equation here, a population equation, and you've got to find the number of mice at the start of the study. Well, that's obviously when t equals 0, so n in that case will be 900 over 3 plus 7, because the e to the 0 will be just 1, and that will give you 90. Okay, so that's that part done. Part B, we've got to find dn by dt. So this is a quotient, it's a fraction, so I take the numerator to be u, and I take the denominator to be, in this case, v. And that v is 3 plus 7e to the minus 0.25t. Okay, now what we do is we differentiate, in this case with respect to t. So that's going to give me 0, because that's just a constant. And this one will give me, well, the 3 will disappear. The derivative of the input of the e value is minus 0.25. So I times through by that. I'm going to write it as minus a quarter. And that gets times by 7e to the minus 0.25t. Let me just double check. Yes, that is right. That is the derivative. Okay, so let me just move this down a little bit. And then what we can do is write out the quotient formula, which is we start with v. We times it by du, which is 0. We take away u multiplied by dv, which is this times this, like that. And that's all divided by v squared, which is 3 plus 7e to the minus 0.25t squared. Okay, great. Now time to do some simplifying. First off, that can go away because that's just 0. Next, we've got 2 negatives here, so that cancels out to be a positive. So I've got 900 on the top. There's a quarter also on the top, so I can just bring that down to make a 4 on the bottom. We've got a 7 on the top, and an e to the minus 0.25t. And on the bottom we've got this thing, and squared, so I'm just going to write it out as 2 separate ones. And I think that will be clear why I'm doing that in a second. Okay, great. Now we've got to convert this into these n. So what I'm going to do is I'm just going to write over here that n is equal to, well, 900 over 3 plus 7e to the minus 2.5t. And let's rearrange that so that we get an expression for 3 plus e to the minus 0.25t, because that's going to equal 900 over n. Okay, and perhaps if I wanted this, then this would be 900 over n minus 3. That could be useful, which in fact is actually the same as 900 over n minus 3n. Yes, I think that works. Yes, it does. Okay, so that's just all little rough working here, and that's going to be helpful, I'm hoping. So let's see if we have any of those already. Well, what we do have is we have a 900 over one of these. So that is, well, that's just n. That is n. Great. So we have an n. And then still on top we have 7, well, let's actually hold up, sorry. Yes, we've got an n, and then we've also got, we know what this is now, don't we? This yellow bit here, this yellow bit is 900 minus 3n over n. Yep, perfect. And on the bottom we've got 4, and we've also got this green bit here. And what's that? That green bit is this green bit here. So that's 900 over n. So down the bottom we have 900 over n. Okay, that's looking a bit more manageable now. Let's just remind ourselves that this was the yellow bit. Yeah, that works nicely. Okay, so what can cancel now? Well, we have an n and a divide by n, so they can cancel. So that's left us with 900 minus 3n over 4 times 900 is 3,600, and that's all over n. Okay, and when we have this little situation here, because we're dividing by a fraction, that's the same as this multiplying up to the numerator. So that becomes n 900 minus 3n over 3,600. And we can divide top and bottom by 3 there. So I can take a 3 out of this bracket, and I can take a 3 out of the denominator. And I think that is what they asked for. Perfect, it is. Yes. So the key here was to just do this little bit working on the side, just to rearrange that n formula into certain different things, which you can then sub in. Lovely. Okay, part C, it says that the rate of growth is a maximum after t months. So we need this function here to be at a maximum. Okay, so perhaps if I just plot that, we can find out what the n value is, which is going to give us a maximum. So we know this has roots at 0 and 300, and it's a negative quadratic, so it's going to look something like this. So the maximum point is going to be at 150. So that's just a bit of a quicker way of finding the maximum rather than differentiating it, setting it equal to 0. So n is equal to 150 gives max dn by dt. So now we need to find the time at which we get to 150 by solving this equation, equal to 150. So 150 is equal to 900 over 3 plus 7 e to the minus 0.25t. Okay, so we can rearrange this to get 3 plus 7 e to the minus 0.25t is equal to 900 over 150, which is 6. So therefore we can say that e to the minus 0.25t is equal to 6 minus 3, which is 3 divided by 7, so 3 over 7. Okay, then we're going to take ln of both sides, which is going to get rid of that e, and it's going to give me this. And then we're going to divide through by minus 0.25. Okay, so let's do that then. Ln of 3 over 7 equals, and then divide by minus 0.25. Great, we get 3.389. Okay, is a maximum after t months. Yeah, I think that's fine to leave it like that as a decimal. According to the model, the maximum number of mice on the island is p. State the value of p. Okay. Right, so we want max n, and let's just have a look at the function n. It's 900 over 3 plus 7e to the minus 0.25t. So in order to make this as big as possible, we want the denominator to be as small as possible. So the max n will occur when 7e to the minus 0.25 tends to 0. And this gives a max n of 900 over 3, which is 300. Okay, obviously I'll never reach that, but that's the limit. Basically, that's the limit. Okay, right, I hope you enjoyed that, and I hope you found it useful. If you did, like, subscribe and share. Thanks very much. Bye for now.